When Descartes first created his analytic geometry in the 1630s, it enabled mathematicians to find the tangent to just about any curve that could be described algebraically. Fermat then showed the connection between that problem and the problem of finding the maximum, minimum of a function. And eventually Newton and Leibniz in the 1680s independently discovered that computing the area underneath a curve is exactly the opposite to finding the tangent. Calculus allows mathematicians to solve easily some previously very hard problems. In this chapter, we will study calculus in detail with a real analysis approach. Let's assume throughout that I is going to be a subset of R, which is an interval. F, which is a function from this interval to the set of real numbers, and C is some point within the interval. The real number L is the derivative of f at C, which we will denote using this notation, if for every epsilon greater than 0, there exists a delta epsilon associated to that epsilon, also positive, such that the difference between this quotient, the differential quotient, and the candidate value L is smaller than epsilon whenever x is within delta epsilon of C, different from C here, and I. And if that actually happens, we will say that f is differentiable at C. Well, what this really says is that the derivative exists if and only if this limit exists. And if that's the case, then the derivative is the value of the limit. If it does exist, f prime at C, the derivative of f at C, is a number, but we can also choose to view f prime as a function. Basically, the function f prime goes from I to R and to every value, and I, it associates the value f prime at x given by this procedure. That's a function of x. For instance, suppose that f is defined from some interval I to R, and C is some point in the interval I, then if the derivative at C exists, it is going to be the limit when x goes to C, f at x minus f at C divided by x minus C. Now we know what f at x is, x cubed. F at C is C cubed, that's the definition of the function f, divided by x minus C. And then you work out the algebra, you get x minus C times x squared plus cx plus c divided by x minus c, cancels out, and then you use the properties of the limit, which we've seen in previous sections. Because this function is continuous, you can just replace x by c. That gives you c squared plus c times c plus c squared, which gives you 3c squared. So this function f prime here would be a function defined by 3 times x squared. Here's theorem 39. Let's say that f has a derivative at c over some interval I, which means here that f is a function from I to R. Then f is continuous at c automatically. It doesn't matter what else is happening to f. If f prime at c exists, then f is continuous at c. But the converse isn't necessarily true. If f is continuous at c, f prime at c does not necessarily exist. It's not too difficult to find such an example. Look at this function here. If x is the absolute value of x, it is definitely continuous at the origin, but it's not differentiable at the origin. It doesn't have a derivative. Now, you know that from calculus because there's a multitude of tangent lines here. But from an analytical perspective, we haven't yet shown the link between the tangent line and the derivative. How do we show this result? I'll let x be any point in your interval, I, assuming that it's not equal to c. In that case, the difference between f at x and f at c is simply going to be f at x minus f at c divided by x minus c times x minus c. Right? Because I'm not dividing by 0 here, because x is not equal to c. This is definitely true. So I can take the limit on both sides. That should be equal. On the one hand, I know that the limit of the first term, f at x minus f at c divided by x minus c when x goes to c, exists, because f has a derivative at c. And I know the limit of x minus c when x goes to c, it exists. So both of the limits exist, and by a theorem we've seen previously, we can distribute the limit to the terms here. This limit exists, as I said, that's f prime at c. This limit also exists, except we can compute its value. If x goes to c, x minus c goes to 0. So what we have is that the limit when x goes to c of f at x minus f at c is f prime at c times 0. We don't care what value f prime at c takes. The only thing that we care about is that it does take on a value. So this product here is 0. So the limit here is actually equal to 0. I can, through the properties of the limit, distribute the limit again. So I end up with the limit when x goes to c of f at x minus, well, the limit when x goes to c of a constant, function f at c. So it gives me f at c. That's equal to 0. And so what I have is that this expression is equal to 0, from which I conclude that the limit of f when x goes to c is f at c. And that's exactly the definition of continuity. F is continuous at c. Now, how would we show that the converse is not always true? I've shown you the function absolute value, and I intimated that because the function doesn't have a tangent at the origin, it's an indication that it is not differentiable at the origin, but we don't know that link exists yet. So do consider the function which is defined by the absolute value. Forget about the geometrical interpretation. We know it's continuous at c equals 0, because the limit when x goes to 0 of the absolute value of x is indeed equal to the absolute value of 0, which is 0. If this function has a derivative, it would have to be given by the limit of the differential quotient when x approaches c. And that would be the limit when x goes to c of the absolute value of x minus the absolute value, well, c isn't just anything, c is 0, minus the absolute value of 0 divided by x minus 0. And this is limit when x goes to 0 of the absolute value of x divided by x. This limit does not exist. So f prime at 0 does not exist. What we get here is that continuity is necessary for differentiability, but it's not sufficient. Perhaps the next natural question is, can you find functions with any number of points where the function is not differentiable? And the answer is yes. I mean, it's fairly easy. You just use combinations of absolute value functions with various horizontal shifts. But there's an amazing result as well. There's going to be functions that are continuous everywhere, but that are nowhere differentiable. Weierstrass was the first one to find such a function. He used the following. Not the most natural arising function, but a function nonetheless. This function is continuous over R, but differentiable nowhere. That was a big surprise at the time.